Okay, I want to make sure I'm recording. Okay, that's recorded. All right, before we start, I have a couple of reminders and announcements. So tomorrow, Thursday, there's going to be a GMI, General Mills info session. I emailed everybody. You should have gotten my email. I just want to make sure that you're aware of. They're going to be talking about, hello, they're going to be talking about opportunities such as internships and jobs. So it's 4:30 to 5:30 session in room 15. After that, there's going to be food, pizza and salad. So stay on, same place. And then from 6 to 7, it's the FSCN club meeting. It's the first meeting of the year. It's good to be there to learn about how you can be involved and what's the benefit of a food science nutrition club. So in my email that I sent, and the first word in the section important, please do not delete. Just go in and read that. It's very brief emails, just tells you what the event is tomorrow. So I just hope you can make it. It's a great opportunity to be involved. Okay, that's the announcement. Okay, the project. So product selection is due to me next Monday, the 19th, but I realize that I might not be able to meet with all of you yet between now and Monday. So as long as you turn in your form, you would have met the requirement of the due date, but you still have to meet with me. So several of you already met with me and selected a product. And if you're late or one of the last ones, you'll get a weird product. Because no two people can work on the same product. So the sooner you connect with me and tell me your availability, we can meet, talk about the project together, select a product, and off you go to the next due date. So please make sure to get that going. Okay. The other thing I want to say, lab attendance is mandatory, while lecture attendance is not mandatory. It would be great if you could come to lecture, but lab, you cannot miss lab. And for any reason you have an event, you're traveling, you know what's coming up, and you want to switch lab, you have to arrange that with me first and let us know. If you're sick that day, let me know, and we'll see how you can make up for the lab. But you cannot miss labs. One last thing, a request from the TAs and Cindy. Please, if you have questions for the TAs or Cindy regarding results of a particular lab, make sure you ask all your questions by Friday. Okay? They usually have other things going on in the weekend. They might not check their emails. So make sure you have all the questions in by Friday. I work Saturdays. I'm here on Saturdays in the office. If you have any questions, you can always ask me, whether it's lab related, lecture related, anything. You can ask me. You don't have to hesitate. Okay? All right. I think these were my announcements and reminders. We can get going. Before I start with today's lecture, which is the sampling and sample preparation, I want to do some recap questions for the previous lecture. Okay, so what's the difference between accuracy and precision? Farah? Huh? Yes, that is correct. So accuracy, how much your values, or how close is your value to the true value, and precision, how close are your application to each other, how small is your standard deviation, and even better, how small is your coefficient of variation. What is the difference between threshold and sensitivity? You want to go for it? You had it mixed up last time.
Well, let's hope I get it right this time.
Okay.
Threshold is the minimum amount that a test can gauge for. Sensitivity is the difference between. I'm sorry.
Yeah, it's the difference is how small of a difference you can detect between two measures. So yeah, your threshold is what's the lowest value you can detect and be confident about, that it's not noise. And sensitivity is how small of a difference the instrument or the assay can, also you can believe that it's true between two measures that are close to each other. In what case CV is better measure of precision than standard deviation? Yes, Sarah? Yes, exactly. So when you have really large mean and small mean and you're comparing two different methods, you can't do that unless you correct for the size of the mean. So that would be when you use a coefficient of variation. What is the difference between systematic error and random error? Vedi?
Systematic error is caused due to the calibration of the system. Like you take a pipette and you calibrate it properly, then that's called systematic error. Random error is because of the temperature, surroundings, things we.
Yeah, that temperature surrounding is one example, but there could be any other number of random things that can be different from day to day, from one experimenter to other, and so on. Give an example of a blunder type of error. Erica? Yes, if you're titrating and you use just a whole different reagent. Yes, that's a blunder. I didn't give this example last time, but here's an example for you to think about significant figure where it is not multiplication, it's addition, and it involves decimal points. So if you have the sum of two numbers is 16.175, and these are the two numbers, what would be your answer in significant figure, Michelle? 16.1718. Why did you choose that? Yes, exactly. So when you're adding, you have to select the one with the lowest decimal point, not the lowest necessarily significant number. Okay? It's for multiplication, you select the one with the lowest number of significant. Speaking of that, it's a request from Cindy to remind everybody that for certain labs, it's really confusing to know how many significant figures you're going to report. And please consult with us, and we will remind you. We will sometimes just say this is how much, how many significant figures you need to report. So sometimes it's very obvious, other times it's complicated, and we'll guide you through it. As long as when you're writing your report, you just don't give so many different figures. Okay. What is a Q-test? What does it do? Drew.
It's a statistical test to determine if something is enough of an outlier to discard it.
Yes, exactly. So it's a test, and there's an equation, and the equation is easy to remember. It's the difference between the outlier and the closest value to the outlier over your range of your data. And if your calculated value is different than a tabulated value for a Q, then you can discard this value and reject that data point. Okay, so again, this is just to help you remember key things from the lecture. We can move on to sampling and sample preparation, which is really important, and in sampling and sample preparation can cause more error than the actual experiment itself. So if you do it wrong, you wasted probably an entire day or entire week or months if you do that wrong. Okay. Check, knowledge check. So to determine quality of a food and its acceptance, it's essential to Ray? Ray chooses F. I haven't read them yet. Hold on. Monitor the okay, another. In the back, is it Agnes in the back? No. Are you? Yeah. Okay. Agnes says E, and I'm going to go with E. So why not A? Okay, so why didn't I agree with Ray first? Because monitor the composition and the characteristic of the whole lot of food product or raw ingredient. A lot can be 100 tons. So do you weigh 100 tons to determine protein content? No, you don't do that. So you have to select a sample. But you may run like grains, 100 tons of grains on a belt, and you can detect for metal. So you can do that. Okay? So depending on your test, but most of the time, 99.99% of the time, you have to select a representative sample of the entire lot. What? All right. For sample preparation prior to analysis, the following is true. For all types of analysis, particle size should be reduced to 20 mesh. Before we answer this, what is the definition of a mesh size? And this is a College Bowl question. Yes, Sarah? Okay, this is you are partially correct. I'll tell you why. Agnes? Huh? What? It's not a whole, it's a square. You're 75% correct. Anybody else wants to correct the answer to 100% correct? So what's confusing in this, it's really the number of square holes per a linear inch. So it's not the number of holes per square inch. It's actually the openings are square. So it's the number of square openings, I should say, not a hole, square opening per linear inch. So the larger this number, the smaller your particle size that can pass through. Okay? And then B, enzyme activity should be eliminated or controlled. Lipid oxidation should be prevented. You're John. Smile. Did I tell you how I differentiate John from Sven? From their smile only. Okay. All of the above. Anybody else? Joe? Yeah, Joe is wiser, older and wiser, so. So, yes. Sorry, John. You'll be wiser one day. Okay, so you wouldn't know this, okay? Don't feel bad, John. You don't know this, but really, it depends on the analysis. Sometimes you need a higher mesh number for analysis, and I'll give you examples. So, okay, so is it feasible to evaluate all foods or all ingredients from a particular lot? Like we said earlier, no, it's not possible unless it's a rapid analytical technique and non-destructive, such as the example I gave you of metal detection. So like, look here, you have a whole truck of grains. Can you analyze all the grains in this truck? No, you can't. So you have a population. Oftentimes, you need to sample, and thus the word sampling, from a population to get representative samples. By representative samples, meaning if you analyze these samples, they are representative of the entire lot. You can make conclusions on the entire lot. So that's what representative. It's very important that you do this correctly so that your estimation is accurate. If you do a mistake in sampling, or your sample is not your lot is not homogeneous, it's heterogeneous, and you do not account for that, you cannot make conclusions on the entire entire lot. So we need to make sure that we reduce our variance. So sampling technique also reduce our variance from evaluation from day to day or sample to sample. And if there's a huge variance, that means you didn't do the sampling correctly. So therefore, because sampling is so important, yes, Ben? Okay, so there is a variation within the population, but there's also variation that could be large due to how you sampled. how you took out a sample and from what region you took out a sample. So let's say you have, let's make it simpler for you. You have a loaf of bread and you're looking for bitterness. If you take from the crust versus taking from the inside of the bread, you're going to have a different flavor profile. So you will have huge variability in your flavor determination, and you cannot assess, if you take a piece of the crust and it's bitter, you cannot say all the bread is bitter. If you're, depending on your objective, you're asking a very good question. Depending on your objective, if your objective to determine differences between crust and crumb flavor, then yes, you want to take a sample from the crust and you want to take a sample from the crumb. But if you're determining, I made a bread, like Amy is going to make bread from a grain called intermediate wheatgrass that has different flavor notes than wheat flour, and she wants to determine which bread is more bitter, then you want to make sure that your sample is homogeneous here and homogeneous there. So again, it's very important. I was going to get into that, but you were ahead of me. Your objective is very important, what you want to determine and why. So sampling plan, it includes a lot of things, and we'll talk about that in a minute. So the sampling plan includes how many samples you're going to pick out. So sample size is not necessarily how big your sample is in weight or size and shape. Sample size is your N value, number of samples that you pick out for testing. Okay, so under this terminology here, sampling plan, when you hear sample size, is how many samples you are taking out. And sampling plan includes your sampling procedure. How are you going to sample? And there's a list of examples in your textbook, in your chapter, to give you an idea how sampling can be done. It can be manually, it can be by mechanically, online. So what kind of tool you use to pull samples out. And not just how you take samples out, how do you select your samples? So there is a statistical sampling where you use random sampling, and there's non-probability sampling. We're going to talk about that. And then a big portion of your sample plan is really how you prepare your samples for analysis. If you prepare them without causing deviation of the constituents, or you have prepared them and you did not account for changes in the constituents themselves when you're preparing your samples, and we'll give examples to that. So your sampling plan, if you want to define it, now that I told you a little bit what it should include, I didn't say everything it should include. So if you want to think about a sampling plan, how would you define it? Okay, Aaron, go ahead.
You'd have to know what defects or flaws you're looking for that you're trying to prevent.
Okay.
You know, how, what part of your, what part
Somebody else wants to answer from your phone.
Sorry, it's on airplane. What part, knowing like, what you're looking for and what part, how best to collect, and like if there's a portion of the population that's more vulnerable than others.
Okay, so your sampling plan, in other words, it does not just include the number of samples and how you pull your samples. It really includes that you clearly specify your objective, and what's your objective, and what defects or what components are you going to be looking for. And then it includes the size of your samples, how many samples, how you're going to collect them, how you're going to prepare them, how you're going to store them. So it is really, it's a document, an organized document for sampling. Not just pulling a sample out, it involves a whole lot of information. And to get to this information, you ask a lot of questions. Okay, so this table here is good to go. I'm not going to go through all of this. This is good to go to table 5.1 in your chapter 5, page 72, to look at, okay, what kind of questions you want to ask. Is this something you want to get an answer simple as reject a lot or accept a lot? Are you looking for a particular quality? Are you determining variability from one product in a 1 day of production or 1 week of production to another week or another month of production? So you ask your questions so that you can define your purpose. And same for what kind of product you're dealing with, and that will determine if you need to homogenize, if you need to dry, how you need to store it, etc. So there's a lot of questions that you would ask, and therefore you would answer in your sampling plan. Now, for your project, you have to put in a sampling procedure or plan, and very short, like a paragraph, for each ingredient you're going to list analysis to, and each and during processing and at the end of the product. Okay, so the sampling plan will be part of your project, and there is example online so that you can see it. And actually, I didn't tell Amy that the sample project is Amy's project. What? When she was a student, and she did get a full mark, so it's a good example. She wasn't paying attention. I know. Your project from food analysis is the example that I have for them. Yes. Okay. Yeah, that's why it was very thorough in that case. Okay. So, and the questions continues, like what kind of methods you want to choose, and that would be, is it a critical or a minor method, and so on. Again, a lot of questions. It's just good for you to go through them on your own and make sense of them. Okay. There are 2 types of sampling in general. So there is something called attribute sampling, and there's something called variable sampling. Attribute sampling is specifically for randomly distributed attributes. Let me give you an example of a randomly distributed attribute. So let's say you have peanuts. What kind of safety concern for peanut? Go ahead, Bill. Yes, but yes, you are very right. But if you have peanuts and you want to make sure it's safe for consumption other than allergies, Farah? Mycotoxins. Mycotoxins are not distributed evenly within your product. Okay? It might be present on one peanut because fungal growth is not uniform. So you might have a fungal growth in some portion of the bag that resulted in production of toxin in some peanuts, but not in others, and you have a whole lot of them. So in this case, what do you think your sample size should be? How many samples, the N, should it be large or should it be small? The number of samples you would pull out for analysis. Mycotoxins, some of them you have 0 tolerance limit for some mycotoxins. You cannot consume them. So the risk of consuming them and getting sick will be.
Calculating risk for the company as far as if they want to be 99% sure they don't have mycotoxins in their peanuts, they're going to do a large sample size.
Yes. And you're touching on another good subject. I was going to, what is the risk? It's 5% usually. They should be at least 95% sure that there is no toxin in their product. So the risk is 5%. Okay, so you're good with that part. So if your risk is so small, you cannot risk more than 5%. So you take a lot of samples, or you take a small number of samples. A lot of samples, because they are randomly distributed, and you want to make sure that you collected random samples from multiple locations in your lot, and a lot of it, to make sure that, okay, all the samples you collected, they don't have that particular mycotoxin. Why is this delayed? Okay, so large sample size. So in this case, when it's an attribute sample, you're mostly looking for presence or absence of a certain variable, and then you decide acceptability, reject the lot, accept the lot. And here the example is not mycotoxin, but mycotoxin is another example. Here is you have Clostridium botulinum in canned food. And sometimes, well, what's the tolerance for Clostridium botulinum? Huh? I heard something. 0. There's no tolerance for it. Okay, but in some cases there is a minimum count of a certain microbe that is acceptable, and sometimes there is, even for mycotoxin, there is a certain tolerance level for a particular mycotoxin. So sometimes you do, you take, in this case it's an organism, you do a measurement. If there is yes or no, if it's there, then you do the count and see if you have, sometimes you should have no count, so 0. Other times, if the count is greater than 0, is it within the acceptable limit? And then you decide if you accept or reject. Okay. Questions so far? No? Okay. So the variable sampling is for normally distributed attributes. So normally distributed attributes such as composition of the sample. So if you take a sample from any place in the lot, it should have the same amount of protein, for example, the same amount of total solids, etc. So these are normally distributed attributes. So in this case, you need a big sample size or a smaller sample size. Smaller. So in this case, you do not really need to pull out a lot of samples because you know that your variable is normally distributed. And it's often for quantitative measurement. It's not like a yes or no answer. Do I reject? Is it there? Is it not there? Do I accept? Do I reject? So it is a quantitative where you have a continuous scale. Continuous scale is like it's 55%, it's like 45.12%, or whatever it is. It's a continuous scale of or a quantitative scale. And based on what you get and your specification for your ingredient or your product, you either accept that quality or reject it. Yep. And here are examples. Selection of sample size sometimes is not only dependent on the type of analysis, sometimes it's mandated. So if it's for nutrition labeling, for example, FDA has specific, the specific regulation on sampling. So for FDA, they go, for nutrition labeling, they tell you you need to pull at least 12 samples, and you need to produce a composite sample from these 12 samples, and then you need to have subsampling 6 subsamples. So that means 6 replication from that composite sample. So that's the requirement for nutrition labeling. So acceptance sampling, so you have a single sampling. You take only a certain number of samples one time. You do the measurement, and then you decide to accept or reject. Double is this example here. Okay, so double is when you take a set of samples, your N, and if your defects, D stands for defects, is the number of defects or defected samples is lower than the acceptable number of defected samples, you accept the lot. If your defects are greater than the number of samples where you would say, okay, I need to reject now, then you reject the lot. If your value or number of defects lies in between the R and A, then you do a second set of sampling, you measure again, and then you decide based on the number of defects. You have another set of acceptable and another set of rejection, number of rejections. So that's called double sampling. And multiple sampling is a continuation of a double sampling. You go a third level and a fourth level of that. Okay, sequential sampling, that's when you take a number of samples and you measure the defects, or the number of, the number of defects. So let's say you took 40 samples and then you measured number of defects and it turned out to be that there are 9. So they lie here. In this region, you reject the lot. If you take 40 samples and you got 3 defects, you continue sampling. You continue sampling. If you then got, after 45 samples, you got 1 defect, then you accept the lot. This is another form of sampling. Yeah, we already kind of answered this before, is if you have a mycotoxins, you need to take many samples. You cannot really do a single sampling plan. It's risky to take just one set of sample. And then in this case, sampling error is many times greater than analytical error. Because if you didn't do the sampling correctly, the risk of accepting a defected lot is greater than your analysis. Sometimes your analysis is really good. You've mastered the method, you have LC-MS, MS to determine mycotoxin, and everything works well. But if your sampling procedure is wrong, even if your data is very precise, it's really not accurate because you have missed detecting your mycotoxin by not sampling adequately. They have to, and if they don't, then their risk of getting, especially when it comes to safety. So like I was telling Andy in a few minutes ago, if they have more than 5% risk that their product's defected, they might risk that somebody gets infected or sick, and that might lead to legal issues and closing of the business. Illnesses, yeah, because people did not do the proper sampling, and that whatever I'm covering here, that doesn't mean that every single company does that, but it's their choice to follow the type of sampling that will ensure that the risk is below what may put them at really high risk of closing or legal issues. Yeah. There we go, consumer risk. So the consumer risk, so if you want to accept a poor quality population, the probability of accepting that from a consumer perspective should be less than 5%. That means that you should be more than 95% confident that your quality is good. From a vendor risk, also it is risky for a producer to reject a lot when it's really not worthy of rejection. They're losing money. So they don't want to do that as well. But they can have a higher risk. So they want to be at least 90% sure that when they're rejecting a lot, that it's really a defective lot. Otherwise, they'll be losing a lot of money if they keep rejecting lots and they're not supposed to be rejected. So yes, sampling is very important, whether it's from a consumer perspective or a vendor perspective. However, while it is important to have a sampling plan, we don't want to complicate our lives, right? It should be simple and flexible based on the need. And it really should protect both consumers and vendors. And most importantly, you need to have reliable results. In order to get reliable results, trustworthy, for sound decisions, your sampling plan should be correct. Here's an example of an AOAC method for sampling from flour that would usually come in bags. And usually your lot would be several bags of flour produced in a particular day. So if you have, for simplicity, you have 100 bags of flour in one lot per one day. So normally you take the square root of the number of sacks in the lot. So if you have 100 bags, for simplicity, you select 10 bags and you do statistical selection, random selection, and we'll talk about that later, how you would select those 10 bags. And from each bag, then you take sample in this way. So you draw a sample from a corner of the bag, diagonal to the center, and then you take another sample from the opposite corner. It's very easy for flour because it's already a homogeneous sample. So 2 samples from one bag of flour, really. And then you store in clean, dry, well-sealed containers until you carry out the analysis. And we'll talk about sample storage later on. So here's where you want to think about homogeneous versus heterogeneous, and that answers Ben's question earlier, is depending on your objective, do you really want to make sure your sample is homogeneous before withdrawing the sample? Or if it's a heterogeneous, how do you take out sample from heterogeneous lot? The bread is an example of a heterogeneous product. Flour is a sample of a homogeneous product. So often when you have a homogeneous product or ingredient, then you can draw a sample from anywhere, like I said for the flour example. But if it's a heterogeneous, you really have to think, what's your objective? Maybe I should homogenize the sample first before drawing out a sample. Or if it's a heterogeneous, then I will pull samples from multiple locations. There's manual sampling, which is prone to human error, and then there's mechanical sampling, which usually continuous, and mostly it's done online during production, that the sample is pulled mechanically. It's less biased, and usually it's done in a timed manner. After, let's say, every hour or every 5 hours, a sample is pulled mechanically. So these are just examples of samplers. Okay, so I mentioned earlier there's non-probability sampling and probability sampling. Non-probability sampling, that means you don't put kind of a statistic, well, not really statistics, but randomly taking out samples to eliminate bias. So here there is bias, but sometimes you are really forced to have non-probability sampling. Oftentimes it's judgment sampling, so you have experienced person who's dealing here, like this guy is going around and selecting samples from a truckload that just deposited the load. And sometimes it's restricted sampling. You have a large silo of whatever corn, or you have a large container of milk, and then you can really only take from the top. You cannot mix the milk to homogenize it, to draw samples from it, and or if it's grain silo, you cannot really reach the bottom or the middle of the silo, so this is restricted sampling. So you cannot really do anything about it. But oftentimes you have the luxury to do probability sampling, and that's the best way to go if you can. Random sampling, let's go back to the flour example, where you have 100 bags of flour and you want to pull 10 bags randomly. How would you do it? You probably heard about this either in school or in any statistics class. How would you, have you heard of random number tables before? Okay. Huh? Yeah. So you assign the bags of flour random numbers, and then you have from a random number table, and then you hold that table and you go this number, and then you look, and then you get that number. So you do that 10 times, and you pull randomly 10 samples. So there's no bias, it's just random. Systematic sampling, that happens mostly online. Like I said, if there is a large production, it's a timed sampling, systematic. It's done after, you can choose your zero time, like 7 a.m. in the morning is your zero time, and from there, every 5 hours, a sample is pulled out for testing. Stratified sampling, let's say you have a company and that company has 10 plants that produce tomato soup. Okay, so then you have subpopulations. So you have 10 different populations, and from each population for a particular week, you can do random sampling. So that's you stratify, basically, your sampling from the different plants that you have. Cluster sampling is similar to stratified. You also have multiple plants, but the only difference is that you assign the plants different numbers and you randomly pick plants to test samples from. Okay? In this case, you just every like 5 or 6 months, a different set of plants are picked for assessing quality. Composite sampling, I already gave you an example where you pick randomly number of samples and you bulk them, and you have a composite sample of multiple samples, and from there you do subsampling for the analysis. And the example I gave you is for nutrition labeling. That's the procedure. You have to come up with a composite sample. So problems in sampling. So the following are potential problems associated with sampling that may result in reduced reliability. So non-statistically viable convenience, poor storage, mislabeling. What, are you guys tired already, Sven? What about you, Bailey? I would go with Bailey. It's all of the above. So really, this statistically viable convenience, non-statistically viable convenience, because the sample you can reach might not be the representative sample of the entire lot. Okay? And then obviously poor storage conditions. We'll talk a little bit more about that. If you subject your samples to heat abuse or humidity or oxygen and air in case of lipid oxidation, then you change the constituents and the characteristics of your sample. Mislabeling, obviously, you label different samples different opposite, and you get opposite incorrect conclusions on these samples. Sample preparation considerations. Particle size, like I said, it's very important to have a certain mesh number for certain measurements. For example, if we are analyzing moisture, protein, or mineral determination, you need a sample to be ground to a mesh number and pass through a mesh number of 20. However, if you're doing extraction assays, you're extracting fat, for example, you need to have at least a 40 mesh. So you need more surface area. So you need your size to be smaller. So yeah, so here's the thing. So sample grinding is also might be a cause of error. So while you're grinding, first of all, you are increasing the surface area and you might lose moisture. So that is something you have to keep in mind. Another time, depending on the grinder that you're using, it might heat up. And when it's heating up, you are losing moisture as well. So that is something to keep in mind. And so when you grind them, you have probably to do that quickly and make sure they don't heat up, and put them in sealed containers. And sometimes you need to flush with nitrogen, and so that you minimize any losses that you might get in moisture or any changes in the constituents. So And oftentimes when your sample is high in fat, for example, or sticky, you cannot grind it, it's high in moisture, so you go with cryogrinding, where you freeze your sample and then you grind it. Again, you have to do this fast because the sample might melt on you while you're doing that. And is there a good way to do it, Sonia? You do cryogrinding. Can you share with... So you use liquid nitrogen, and then how fast can you do that?
It takes about 10 15 minutes per sample. So you have a frozen metal rod inside a container, and then it basically shakes it until everything is blasted to smithereens, but it's done in a liquid nitrogen environment.
So it stays,
Everything.
yeah, it stays frozen, huh? Can you raise your voice so that the whole class can hear?
You do it in a liquid nitrogen environment, so you have like a metal rod inside a container, and so everything stays frozen. So it takes like 10 to 15 minutes, and the trick with it is that once you do that, you have to keep your sample frozen, otherwise it'll all stick together and get nasty. So.
Yeah. Okay, and sometimes you have mills that have built-in compartments where you have sieves. Do we have the OD mill is set up like that?
No, we have one of those down in the grade lab.
What is it? Rototap? We do have one? Yeah? Okay, so then you can decide what mesh you would put in there with different mesh numbers to select the size for your final sample. We have a couple more minutes, so I'll go through this. So we need to eliminate enzyme activity or control it. Do you know why and how we would do that? Sonia?
If there's enzyme activity, it could change your sample.
Yeah. If you have enzyme activity, like you have lipoxygenase, for example, you get lipid oxidation. If you have lipases, fat is dehydrolyzed, you have proteases, protein is hydrolyzed, you change your flavor, you change your color, you change a lot of things in the constituents. How do you do that? Sven? Temperature control, humidity control, so you might store in refrigerated conditions. Sometimes you have to store under freezers, in freezer conditions, like minus 20 degrees. So, or sometimes you heat actually to eliminate the enzyme, to inactivate the enzyme.
Stored it under modified atmosphere.
Yeah, so you could store in modified atmosphere. With that, we mean controlled humidity, controlled oxygen, and controlled temperature.
Using, like say, nitrogen or other gases?
Yeah, that would be for under this to avoid lipid oxidation. You can flush with nitrogen to remove the oxygen. For example, you can add antioxidants to prevent oxidation during storage of your sample. So you can do that. And also you want to limit microbial growth, because not just for safety, microbial growth can also lead to production of extra enzymes actually. And microbes also use up some of the components for them to grow. So you are changing the composition of your sample again. How to do that? Sometimes you add antimicrobial agents. So you add, or you store under controlled humidity and temperature. So basically, you do not want to alter your sample. You have to, once you prepare your sample, you have to store it in a way that it's not altered until analysis. And it's often recommended that you do not store for a long time. So if you extract oil, for example, to do later on oil characterization, you don't want to store it even at freezers, because lipid oxidation can happen also under low temperature. So you really don't want to store them for a long time. Before you go, this is an assignment. If you want extra credit, 5 points extra credit, please bring it to class on, I'm going to say Monday. I'll give you till the weekend. Turn it in, and it's for a +5. And next time we'll do the recap questions. All right, thank you. See you on Friday.